Hi everyone. So I want to, now that we've finished the talking about the trend in ionization energy and the explanation for that trend, as well as the explanation for a couple of the exception in the trend in ionization energy, I want to quickly talk about the other trends that we also observe in the periodic table for different elements, and these are trends in electron affinity, which is increasing electron affinity from left to right and top to bottom to top. But electron affinity, as you'll see in a second, is actually defined as an exothermic reaction. So you'll see that that when it goes from left to right, it's really saying that it is gaining more and more energy as that process happens. Another property we'll talk about is atomic radius, that the radius goes bigger and bigger as you go from top to bottom, and it goes bigger and bigger as well as you go from right to left in this case. Another property we'll talk about is something called metallic character, which is basically the idea that metals tend to conduct electricity and heat very well, they're malleable and so on. And what we notice is that as we go from basically the top right here to the bottom left, the metallic character is increasing. So in other words, you're getting more, things looking more and more like metals, whereas when you go up to the top here, things look a lot like nonmetals, which is the fact that they don't conduct electricity, they don't conduct heat, and they're not malleable. Okay, so we'll try to explain some of these things again, but I really want you to kind of master those explanations that I mentioned about the ionization energy, not so much that you can, basically memorize and explain it again to me, but more importantly, using the same reasoning that I use in the ionization energy explanation to explain these properties as well. So we're now going to go to electron affinity, which is usually the second trend that most textbooks would talk about. And electron affinity is, again, a particular type of energy, and this is in this case an energy that accompanies the process of electron gain for a gaseous atom or ion. So when we talk about ionization energy, we define that as the energy needed to remove an electron. Electron affinity is the opposite process, the energy that accompanies an electron gain. Okay, so it turns out that for most atoms, the electron affinity energy is usually negative. Okay, however, we can have both negative and positive values for electron affinity, but again, like I said, majority of cases these are actually negative. So examples, some of the examples are shown here. The reaction would be written this way. So you'll write the atom plus the electron, because you're gaining electron in this case, plus the electron, and then you form that anion in this case. So notice the exact opposite is what we did for ionization energy, because in ionization energy you're losing an electron, so you're forming a cation in this case. So in electron affinity you're forming an anion, and the first electron affinity would correspond to the energy that you gain from adding that first electron. Okay, so if add, for example, for the case of chlorine going to chloride, you actually gain, in this case, gain meaning that you become more stable. Okay, so you actually the first electron affinity is actually a negative 349 kilojoules per mole. This is obviously an exothermic energy. That means that the system actually becomes more stable by 349 kilojoules of energy, right? So if you think about an energy diagram, the type that we used to draw quite a bit in topic 6 when we talk about thermodynamics, you have an energy of the atom somewhere at this level higher, and then you have the energy of the ion somewhere below here, and the difference between those two energies is 349 kilojoules per mole. Okay, so the ion is at the bottom, is more stable than the atom. Oxygen is negative 142 kilojoules per mole. Not as, you don't gain as much for oxygen in terms of stability as you do for chlorine. Now when you get to nitrogen, in fact, it actually becomes a positive value. In other words, nitrogen really doesn't like to form this N minus ion, because it actually is becoming an endothermic process as a result. Okay, so it's something that you want to keep in mind But again, the majority of the time, the values of electron affinity is negative. Now, let's take a look at the trend real quick for electron affinity. Okay, here's sort of a partial list of what the trend of electron affinity energy is for a for elements in the periodic table. And really, we're kind of cutting this off at around 20, which is up till about calcium. So what you notice here is that generally, as you go across the period, okay, across the period, in this case, you'll have to look at something like from lithium, for example, to fluorine. Okay, so that's a period, right? That's period 2. This is period 2 right here. As you go, you notice that generally speaking, things tend to come down, right? So you can see there's fluctuation, obviously, but generally things tend to come down. So in other words, it becomes, when I say come down, I really mean it becomes more negative, okay? So when I say it becomes more negative, what that implies, of course, is that as you gain, when you gain that electron, it becomes more and more exothermic, or more and more it's better and better to do that. In other words, gaining electron becomes a better process as you go from left to right in the period. Okay, so in other words, gaining an electron for fluorine, the fluorine atom, is a great thing. It's not so great for lithium, but it's still okay. It's still a negative process, right? It's still a negative energy process, still an exothermic process. You see the same pattern when you go to period 3 here, when you go from sodium to chlorine. Same thing, right? Overall, you see a drop in electron affinity energy, so more negative. So that means again that the electron affinity actually becomes better and better as you go from left to right. Now, on the other hand, when you go from, you compare hydrogen, lithium, sodium, and potassium, you notice that overall there's a bit of an increase. Okay, there's a bit of an increase. In other words, it gets less and less negative. Okay, it becomes less and less exothermic as you go from left to right in terms of electron affinity. So this is what we have to explain using the same reasoning that we used to explain ionization energy, which was the equation, the binding energy equation. So we want to think about what is the effect on Z effective, what is the effect on N, what is the effect on orbital penetration and shielding as we go from left to right and as we go from top to bottom. Well, I'm going to pop up the slide now. If you look at a couple of the first sentences here, they're really exactly identical to what I used when I talked about trends in ionization energy. Because what's going on when we go left to right or top to bottom is exactly the same, right? The only thing that's different is how that affects that particular property, in this case electron affinity. Okay, but when we go top to bottom, we have the same exact thing that happened when we go top to bottom for anything, which is Z is going to go up, N is going to go up, shielding is going to go up, and as a result, as we said before, the Z effective stay about the same, but the N keeps going up, and that makes the binding energy less and less exothermic, which makes the electron less and less stable. Okay, so if you look at this explanation, binding energy becomes more positive, in other words, less stable electron, which means now we want to kind of get into the specific part about the electron affinity, because electron affinity means adding an electron, right? So if your electron is not as stable, adding another electron has to be difficult to do, because the electron that you already have is already not that stable. So trying to add another one should not be easy, should be difficult. If it's difficult, that means your electron affinity energy should be less exothermic, right? Because remember, think about it. Difficult really means energetically costly. Okay, so if it's not, if it's less easy to do it, that means it's also less exothermic, because you kind of want to correlate that word easy, energetically easy, to the word exothermic, and energetically difficult to the word endothermic. So in this case, when we say it's more difficult or less easy, it really means less exothermic electron affinity. Now when we go left to right, on the other hand, as we said before, Z increases, but N stays about the same. And in fact stays the same because you're on the same shell. So shielding is about the same. You don't really get that much of a change. You don't get the change in the shell number, but you do get a change in the atomic number, which makes the electron more stable. So if the electron is more stable, that means the binding energy is more negative. If it's a more stable electron, that means that when you want to add another electron, it should be easier to do because your electron becomes more and more stable. Okay, if it's is easier to do, that means the electron affinity is more exothermic. And again, there's certain effects of orbital type, i.e. orbital penetration. You know, again, if you're adding to an s versus a p orbital, for example, there might be differences in electron affinity energy. There might be exceptions, but the way you would explain these exceptions would be exactly the same as the way I explain those exceptions in ionization energy. Okay, so hopefully this explanation makes sense to you, and if it doesn't, you should really look back at the explanation for the ionization energy, because that's really where I spend you know, a lot of time really going into detail about exactly why something happens and what the explanation is. So I don't want to repeat all of those again, because it's the same idea applied to electron affinity in this case. Next property I want to talk about is atomic radii, and this is usually fairly easy for students to understand. When you look at the sizes here, you can clearly see that as you go down, things get larger, and as you go left to right, things get smaller. The question is why? Well, again, same idea. When you come down, atomic number increases, but the principal quantum number increases more, right? Because of the shielding and everything. And as a result, okay, using the same exact sentences I used before, but only changing this third part here, the electron binding energy becomes more positive, which is less stable. A less stable electron is an electron that doesn't interact with the nucleus as strongly. In other words, its electrostatic interaction is weaker. If it's weaker, that means it must be a more distant, right? An electron that's further away from the nucleus. Okay, if it's further away, that means the atom must be a larger atom, right? That should make sense to you, hopefully. If it's a weaker electrostatic attraction, the distance of that electron must be far. If it's far, that means it's a larger atom. Similarly, when we go left to right, same two factors, Z increases and stays the same, but overall the binding energy becomes more negative. And if it's more negative, that means that the electron is more stable. Well, think about what the meaning of that word is, electron more stable. Electron becomes more stable because of its attraction to the nucleus. So if the electron becomes more stable, it must be closer to the nucleus. If it's closer to the nucleus, it must have meant that this is a smaller atom. So then that explains why we see smaller going left to right and bigger as we go top to bottom. The trend in metallic character is actually not that hard to explain. Think about it. A metal is something that tends to form cations, right? Whereas a non-metal is something that tends to form anions. Okay, if you think about it from that perspective, it should be easy to explain that based on your idea of ionization energy and electron affinity. Again, what we said before is that ionization energy increases as you go left to right, which means that it gets harder and harder to remove an electron. Now, when you remove an electron, your atom becomes a cation. So if the ionization energy goes up from left to right, that means it gets harder and harder to remove that electron, which implies that it gets harder and harder to make a cation. And that makes sense because when you go to the non-metal, these guys don't form cations, they form anions. Now, if you look at the electron affinity, on the other hand, the electron affinity gets better and better and better, right? You get more and more exothermic. And remember what electron affinity corresponds to. It corresponds to the energy you gain as a result of forming an anion, getting an electron. So in other words, what these trends are saying is that as you go from left to right, your chances of forming a cation gets smaller and smaller. On the other hand, your chances of forming an anion gets better and better and better. And that makes sense with the metallic versus non-metallic character. Vice versa, when you go right to left, right, it's easier to form a cation. Ionization energy is less, but it's harder to form an anion because the electron affinity is less exothermic.